In the world today, PVC is one of the most important petrochemicals. It has many uses, including clothing, electrical cable insulation, and pipes. But how is PVC made? It starts with polymerizing VCM, the vinyl chloride monomer, and we have a design proposal for the manufacture of VCM. But how did we simulate this?
Let's ask a member of the Patronomers.
I'm the chemical engineering manager, and we use Aspen to simulate our proposed process. Let me give you a comprehensive overview of our simulation.
When running our simulation in Aspen, we have to choose a global overall model as well as a specific localized model. This is done to represent the compositions, enthalpies, and model behaviors present accurately. The global model chosen was Wilson as opposed to NRTL and Peng-Robertson due to it having the lowest error in measuring those parameters. This was the case in multiple literature sources. In oxychlorination, feedstock ethylene and oxygen are reacted with recycled HCl. The main product formed is EDC, however due to side reactions, water, CO2 and TCE are also produced. The reactor operates at 230 degrees Celsius and 1.5 bar. The thermodynamic model chosen for this was SR polar. This is used in ideal mixture systems with non-polar and mildly polar compounds. We also considered PRWS, which shares similar properties to SR polar, however the error found in PRWS was slightly higher when compared to SR polar. In direct chlorination, feedstock ethylene and chlorine are reacted to produce EDC. The operating conditions are 85 degrees Celsius and 1 bar. Due to the system being non-ideal and having highly polar molecules, an activity coefficient model such as UNIFAC is used to represent the system. UNIFAC was considered, but it was only accurate at pressures over 10 bar. After mixing the products from direct chlorination, oxychlorination, and the EDC recycle stream from VCM purification, we can purify the EDC mixture. The first column separates light products from the EDC, and this operates at 79 degrees Celsius at the top and 83 degrees Celsius at the bottom. The second column separates EDC from heavy products such as water. This operates at 83 degrees Celsius at the top and 91 degrees Celsius at the bottom. All reboilers and condensers for columns operate at 1 bar. The pyrolysis reactor operates at 500 degrees Celsius and 20 bar. Its main function is to crack EDC into VCM and HCl. The first column separates the HCl from heavy products such as EDC and VCM. It operates at 0 degrees Celsius at the bottom and minus 85 degrees Celsius at the top. The second column separates the EDC and VCM. It operates at 83 degrees Celsius at the bottom and minus 14 degrees Celsius at the top. The output VCM purity is at 99.8%. In Aspen, you can choose to use various models to represent each reactor and distillation column. We chose to use R stoich for the reactors. This is to allow us to define multiple reactions with fractional conversions being stated. Also, the heat of reaction can be calculated from this model. Other considerations will R yield, however due to the lack of stoichiometric inputs, heat of reaction would not be calculated. The columns were modeled using DSTWU due to the fact that it is a reasonable initial estimate, and when compared to literature values the results were similar. The simulation runs with no errors but with some physical property warnings. These are likely to be caused by the thermodynamic models representing non-ideal mixtures.
In order to carry out the energy analysis, the streams that needed further energy to be cooled or heated were identified using the duties calculated from Aspen. After doing so, a graphical representation of the streams was made. A delta T-min of 10 degrees Celsius was used in order to carry out the pinch analysis. The streams highlighted will need heat integration. In order to determine the pinch point, a composite curve was plotted. The composite curves are on a DH diagram in which the temperature axis is divided into intervals depending on supply and target temperatures of the process. As seen from the graph, the streams which consume the largest amount of energy are streams 34 from cooling and 31 from heating. These streams leave and enter the pyrolysis reactor respectively. After heat integration, it is evident that the heat duties required for these streams has decreased. From the pinch analysis, we can construct a heat exchanger network. This can then be implemented on Aspen. The hot stream for the reactor enters the heat exchanger. This is to heat up the cold stream entering the heat exchanger. This in turn leads to an overall reduction in the energy consumption of the utilities. In terms of savings, the process requires 30% less energy and the payback period is 3 years, making it sustainable. As for the utilities, cold water, hot water, high pressure steam and fuel or natural gas were used to reach the target temperature. The total savings on the fuels were estimated to be 43%. In conclusion, the thermodynamic models chosen for this process were allocated based on the mixture as well as the operating conditions. DSTW is a reasonable initial estimate and R stoich enables us to receive the enthalpy heat of reaction. Overall, with heat integration, there is a 30% heat reduction, making the process more sustainable, thus leading to a 43% saving on utilities usage.
So there we have it. Thanks for all your attention.